really like R. Today is logarithms. I promise you it's not hard. I'm thinking you guys found Fridays pretty easy. You just figure out the equation from the axes, write it down, plug in something, and kind of undo. That's the same thing as today. We just have to remember about the Guinan circle. If you did not have me for math 3, that would not make sense. But if you did have me for math 3, you'll know exactly what I'm talking about with the Guinan circle. So I think Miss Rice called it the loop-de-loop, the log loop-de-loop. Okay, anyway. What did Mr. Knight call it, you know? He doesn't play with our little okay. Yeah. He doesn't make up little dumb things for math. But anyway, okay. So okay. So the first thing we're going to do is work on the power model. Power model is specifically logging both X and Y. I'm not going to ever ask you what the name of it is though. So all I really need you to do is identify the axes and what's happening. So find your resource page for 3.3b that says transforming with logarithms. First one has the power model. Okay, and this is that rockfish data again. Okay, so I want to kind of go through, I know that I'm kind of lame and I try to make this like you're watching a movie, I don't know, but just play along. Okay, so there's like researchers in the stream, right, with their safari outfits, and they catch these fish in a very humane way. I don't know, whatever that is. And then they measure how long they are, and then they weigh them, and then somehow either go back to some kind of lab, computer, something, or give it to researchers, other people. I don't know how this works because I just work here, but let's pretend they got this data and they grabbed it and it made a curve and they're like, oh no, okay. So all that work we did with the frogfish and the weighing and the stream and the, anyway. So then they mess around with the data in the table and they log both X and log both Y and they get a line and they're like, okay, good, we can work with this. Does that make sense so far? Okay, and then they do the extra work of creating a residual plot so they can really analyze the form. And this has no pattern and even scatter, which means that it's linear enough to call linear. I mean, you can kind of tell from that, but just keeping you up on where we are. So they came back from the stream. Their raw data was a curve. Oh no. They logged both the X's and the Y's. They got a line. They're happy. And then they just double check themselves with a residual plot to make sure there was no pattern in that. Okay, so now you're caught up. Okay, so now scroll your eyes down to the output data at the bottom, and we're going to do the highlighting and labeling thing that we do. And my goal with the highlighting really is to focus your eyes only on these 4 numbers. I don't want you to get confused and use any of the other numbers because we don't use them. We don't ever use the standard error coefficients. That's a lie. Actually, we use them in chapter 12 for like a hot 30 seconds. The t-values and the p-values again, chapter 12. But and this guy, I've never seen him used in class. I'm sure they do something with this in industry, but I don't know, not in stats class. So these are the 4 that we are focused on. I just want to remind you the top one is A because it says constant. The bottom one is B, that's the slope. And whatever is listed next to the slope is the X, and the other thing is the Y. And you're like, I don't need that because there was a graph up there, but sometimes there's not a graph. So you need to be able to pick that apart. Okay. Any questions about my labeling? Are we getting good at that now? Better? Okay. So now back to here. Based on the graphs, why would it be reasonable to use a power model to describe the relationship between weight and length? Okay, we're going to say two things. It is reasonable because you really only need one of the two of these, but we have two, so we're going to do both. First, the transform scatter plot is linear. Okay, so what I mean by that is this curve, your original data, is now a line. Does that make sense? Okay, or this is going to be an and or situation for us. You only need one of the two of these, but we have both. The residual plot shows no pattern and even scatter, which means that the form is linear. I want to be very clear. The only way you can get the form is from a graph. You cannot assume the form from numbers. Okay, next question. State the equation of the least squares regression line to find any variables you use. Okay, so do you guys notice that both the x and the y are logged? Okay, so this is gonna feel a little strange. So log of y. And I double checked myself in the book. The hat goes over the whole thing. Equals a is negative 1.900 plus b is 3.049. And then do you notice how x is also logged? So you say log of x. Any questions about that? So you saw a log and y. A log was on both x and y. Okay, and then we still need to define our variables. So x equals length in centimeters. Y hat equals predicted weight in grams. Speaking of which, funny story. You know, I showed you the video of with the George Washington and the weights and measures. Yeah. Well, I put it in my YouTube video. I wasn't even thinking about it, and YouTube blocked the whole thing because it was like copyrighted material. So I had to refilm everything in fifth period without the video in it. I still showed them the video because it's funny, but I was like, oops. I'm glad I didn't get blocked. Oopsie. Okay. Use a model from part B to predict the weight of a rockfish that's 36 centimeters. So x equals 36 centimeters. Log of y hat 1.900 plus 3.049. I don't really want a parenthesis there. log 36. Okay, calculator time. So I'm just going to type in this part. Remind yourself where the log button lives on your calculator. It's right next to the 7. $2.845. Okay, now I'm gonna switch colors. If you're a person who writes your notes in different colors, I'm gonna switch colors on purpose. Math 3 question. What is the base of a log when there's no base written? 10. Look at all of you and your retention. Okay, so I'm gonna put the 10 in, and then I'm gonna draw the Guinan circle or the loop-de-loop or whatever your teacher said. Okay, rewrite it into exponential form. So 10 to the 2.845 equals y hat. Rewrite to exponential and then calculator again. $699.842 grams equals y hat. All right, you guys set up example 2. We just need to do natural log and then we're done. This is not the end, but it's not bad, I promise. Okay, so when you're done writing, I want you to take a look at the last stage of this in the packet. So just flip the page over. Last one. What do you notice about the original data? What's the form? Exponential, right? Non-linear, definitely exponential. So the book had to change their context on this one because they were dealing with exponential specifically. So this is a very interesting case. It's actually the number of years since 1970 on the x-axis, and then the number of transistors manufactured because of computer production and phone production. Like all of our technology has transistors in it. So the number of transistors being manufactured is exponential. You can imagine why. But okay, so to answer the first question, so take a look at the second scatter plot. So I'm going to ask you two questions. Is it a reasonable model looking at the second scatter plot? Yes. Okay, it's linear-ish, good enough. So what should we say? Look up at your notes in example 1A. What should we say? It is reasonable because why? Yep, beautiful. Okay, they did not give us a residual plot on this one. It's okay. We just need one or the other. State the equation of the least squares regression line to find any variables you use. Okay, so we're going to go back to last time, do our highlighting. Notice they're giving you less and less. This is still A, this is still B, this is still X. So after you label that and highlight whatever you need, go back to the transform scatter plot and tell me what transformation did they do? Natural log of y. Natural log of y. Everybody good with that? Can you all see the natural log of y? Yes? And you see x is plane? Everybody see natural log of y and x is plane? Yeah? You sure? Okay. All right. So natural log of y equals 7.227 plus 0.354 x x equals years since 1970. Y hat equals predicted amount of transistors. Can anyone see where this is going? Can you see? Are you picking up what I'm laying down? What's going to happen? What do you think? Predict for me what's going to happen. We're going to take some number and plug it in for X, and then solve for Y with doing a base. Nice. Oh, sorry. Okay, this is the end. I told you it wasn't too bad. Not too bad. Definitely doing some math 3 today, though. Okay, so here's my question. Do I plug 2020 in for X? No, what is X specifically? Years since 1970. Okay, so what is X? 50. Okay. Really close, guys. Let me finish. Okay, so we got 24.927. Okay, and what is the base of natural log? E. Guidance circle. E to the 24.927 equals y hat. Okay, so remind yourself how to do that on your calculator. It's second natural log. Almost forgot my context. Really quick, you're going to have answers in scientific notation in stats. It happens a lot because you're working with like measurements and biology, percent of something in a stream, like teeny tiny amounts. Don't get freaked out by scientific notation. The more it happens, the less freaked out you'll be. You're not wrong. It's just because of science. We'll blame them. Mr. Sinat's fault. Yeah. Just kidding. I love him. Okay. All right, last thing, which model works best? So sometimes they're going to give you multiple representations. So for example, what I mean is, like in the rockfish deal we just did, they transformed it a bunch of different times. So they did the powers, they did the roots, and they did the log of both x and y. And which model works best? So there's two things you want to look for, and it's not really going to be that shocking. Pick the one that looks most like a line. Duh. Or this is going to be really bad grammar. I don't know how to say it any other way. Guess the one that looks the most random. Most no pattern and even scatter. Most evenly scattered. Most I don't know how to say that right, but now there's one thing that you might notice I did not say. Did I say check the R squared values and find the one that was closest to what? No, I did not. Why? Because you cannot use numbers to establish form. It has to be a graph. Can you use that to help you back up your evidence? Sure. But remember, the software and the calculator will calculate those even if it's not linear. It will still do it. It doesn't have the brain you have to take a look at the graphs and analyze it. It's just going to do it. So can you use the R squared? Sure, just be careful. Use at your own risk, basically. Is there anything else I wanted to say? I don't think so. Oh, I do have a joke, and I think it's really good. It's for those of you in psych, you'll like it better than everyone else, but okay. Here's your homework, 85 to 91 odd, 95 and 96. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Do you get it? Because that didn't cause him to learn that. Rod would like this joke.